So let's look at an example. What's going to happen here? Okay, so we have a mass that's going to slide down and negotiate this circular arc of radius r, and there's no friction. We're in ice world, and then it's going to run into a spring. So play the movie for me. What's going to happen? It will slide down, compress the spring. Yeah, you have it. Say it. It goes down like that and compresses the spring. Then what? Then it's going to bounce and go back up. Yeah, okay. So this is a way of making a clock, right? A really crappy clock, right? Yes, okay. All right. A really crappy clock. Okay, so I want to figure out how much the spring will be compressed at maximum. Okay, and I want to use the ideas that we were just reviewing on work energy. That's kind of a small radius. Let's beef that up a bit. Sorry for the vegetarians. Okay, so I think this is supposed to be h, and I'm really neglecting the size of my mass, which is now over there. Okay, so m, and then the spring happens over here. Okay, so the work energy theorem says that the change in the kinetic energy is due to the net force on the object. So let me isolate the object during this segment. So here it is. The net force, there's just gravity. What about normal force? I could put it in, and there's nothing against, and so it will be 0 on this segment. Okay? So as the particle moves down through this distance h, the net force is mg. The work done by gravity will be the integral of that force dotted into the displacement. Is the displacement parallel to the force? Yeah, so this is going to simplify. Maybe I'll use a coordinate system where y is up and x is to the right. I know that looks really original. All right, so then I would have mg in the minus y direction. I could also distribute the minus sign out. And what is the displacement dr? So it's only moving in the y direction. And this is a little bit of a trick. I can either put the direction in the limits, or I can embed it over here. I'm going to put it in the limits because we're going from someplace. We're going from, a distance up. Let's call this the 0. So I'm starting at h plus r, and I'm ending y where? At r. Okay, so everything in this integrand is a constant, so I can pull it out. I have minus mg, y unit vector dot y unit vector is just 1. And I get the integral of dy, so that's y to be evaluated between the initial and the final position. So let's just hope that having done this, were you expecting positive work that gravity did as it fell? The kinetic energy to go up? I hope. So let's see how this goes. Minus mg times r minus h plus r So that looks a whole lot like MGH. As it better, right? It's fallen down a distance h. Gravity did work on it to the tune of mgh, which we recognize also as, okay, that's the change in the potential energy. And we're going to see, under what circumstances we can define a potential energy. But we know we can do that for gravity. Now, what happens on the arc? We get a new force. Yeah, we have a normal force. So why don't we care? So why we're going to develop a normal force for the rest of the motion? Why does it not matter? It doesn't do any work, he says. Okay, so I'm going to pick some sort of random point on the arc. And we're going to have a normal force up, and we'll have gravity down. Is there anything else? No friction on this part, so that's it, right? So the displacement is going to be like that. And it's everywhere along that circular arc. In fact, everywhere on the circular part and then even on the ground, the normal force is normal to the direction of motion. Hey, what a good idea for a name. Yeah, okay, so n dot ds is always 0 for this motion. So it does no work. So how fast is it going to be going by the time it gets to the bottom? Well, it's now getting to fall another distance r. So I assume you'll be okay with the kinetic energy, 1/2 mv squared at the bottom will now be equal to mgh plus r. In the, before it hits the spring, before contacting spring. Now it contacts the spring, and it gets a new force on it, and that force is going to be applied this way. And it's going to be worth kx if I measure x from where?
From when it touches, where it first touches the spring.
Yeah, we have to assume that this is the unstretched length, and so if I measure x with respect to that position, then the kinetic energy, the potential energy in the spring, or the force of the spring will be that. Yeah, think first, speak later. Nah, that's no fun. All right, so now we want to know the work done by the spring, which will be the integral of the force the spring supplies dotted into the displacement. Yeah, whatever. Okay. So the spring force, the displacement is going to go that way, and the spring force is going the other way. And so what do I get? I get the integral from x is 0 to some maximum compression of kx is the magnitude of the force. It's in the negative x direction. dr is going to be dx, and that's in the x hat direction. Now I can't pull everything out of the integral, but I have a minus k that comes out of the integral. And I have the integral of x dx from 0 to some x final. at maximum compression. So that's going to be minus 1/2 K X final is the work done by the spring. So it will come to rest when the spring has done exactly as much work on the mass as gravity did. So the maximum compression will happen. Let me just carve out a little space here. So when the kinetic energy is 0, mg h plus r is now 1/2 K x final squared. So x final squared would be, let's see, 2mg h plus r divide by K, and then do eraser physics and just put the square root.